This set now looks like a single resistor, whose value is R2 parallel R3 plus R4, because this parallel combination is in series with that. And then this single resistor, which is what that looks like there, is in parallel with R1. And so our final result is, it's a little complicated, but very simple to write. And that is that R1 is in parallel with the combination R2 and R3, which is in series with R4. Well, I want to use those results to solve a circuit the easy way. And this is actually a pretty practical circuit. So what I want to point out here is that this is the system we've already been talking about. Okay? And what usually happens is when you try to pass that signal onto the sink, that it has an input resistance. In some sense, its equivalent resistance is something which we're going to call R sub L, and L means load. And the question is, does the relationship between Vin and Vout change because there's a load resistance out there? And you might say, well, geez, this voltage here is the same as that voltage there, so probably it doesn't change. Well, that's not quite true. That's because these are in parallel, and these voltages are actually across the parallel combination. There's something to figure out there. I've essentially given away how you analyze it. What we discover is that the output voltage is, using our series and parallel combination rules, this looks like a single resistor, which is R2 in parallel with RL, and then that's in series with R1. So we simply use voltage divider to figure it out. And this is the concise expression, and when you simplify everything, you get this for our final answer. Well, that doesn't much look like the result that we had before, which was R2 over R1 plus R2 times Vn. So when is there a situation as we change RL that this result looks like that? If you think about that for a second, there's sort of two extremes to look at. RL going to 0, RL going to infinity. That's the easy cases to look at. It was pretty clear if you had set RL to 0, the output is 0 volts, right? Because there's an RL in the numerator. More interesting is RL going to infinity. When RL goes to infinity, this term down here essentially disappears because these terms are getting big, and then the RLs cancel, and sure enough, you get this result. So, if you want to develop a system such that when you attach it to the sink, it has a input resistance RL, it better be that RL is big. And it's going to take until the succeeding video we define what big in comparison to what is. That's in the next video. All right. So, in summarize the resistor equivalence. So, if you have resistors in series, the equivalent resistance looks like the sum. And voltage divider, what it looks like, the voltage across any one of them is that resistance divided by the sum of all the resistances. If you have a lot of resistors in parallel, the equivalent conductance is the sum of the conductances, and the current through any one of them is that conductance divided by the sum of the conductances. So it turns out writing the current divider rule, which is what this is over here, in terms of conductances makes it look a lot like the voltage divider up here. Is when you write it in terms of resistances, the expressions get complicated. It's a whole lot easier to write it in terms of the conductances in this case. By the way, there's a minor error on this slide. There should be a voltage V here and an I there. Okay. So, That's what we've learned about solving circuits. The equivalent resistance idea comes up because you ask the question, what does the source see? And it turns out, as you can see from all these examples, when you use the idea of an equivalent resistance, along with the ideas of voltage divider and current divider, you can solve circuits rather quickly. And notice we solved that circuit having the load resistor on it without ever writing KVL, KCL, or the VI relations. We just wrote down the answer. That's really very, very nice. So the whole idea about being able to solve circuits easily means seeing the structure, what's in series with what, what's in parallel with what, and finding the equivalent resistances accordingly.